IBM has made a multi-billion-dollar investment in quantum computing, recognizing it as a next-generation technology. They are currently working with Fortune 500 companies worldwide on early quantum computing use cases. These companies include major banks, retailers, manufacturers, and more. These new use cases provide a distinct competitive advantage to IBM as the leading company developing quantum computing hardware and software. IBM has identified quantum computing as a strategic project and a significant differentiator in the marketplace, and is currently training clients in the Qiskit programming language on the IBM Quantum Experience. It's clear that quantum computing represents a fundamentally new approach to data security, but few people realize the dangers that quantum computers pose to confidential data. In this presentation, I'll discuss the Latlock project, an accessible way to use quantum-resistant encryption methods to protect files on your computer. Quantum computers can't crack traditional encryption methods yet, but there is a theoretical method called Shor's algorithm by which most data would be made vulnerable. Shor's algorithm works by quickly finding the prime factors of any integer. For example, if we're given the number 21, Shor's algorithm can derive that the two prime factors of 21 are 3 and 7. Now, for a problem like this, it's pretty simple to find the prime factors of an integer. It's just two integers, and that's totally fine. But as numbers get bigger and bigger, it becomes more and more difficult to find their prime factor. That's where Shor's algorithm comes in. When you're using a quantum computer, you can use Shor's algorithm as well to make it really effective at finding these prime factors. So much more effective than anything we've ever seen before, any sort of traditional computer. Now, this may seem great at first. We can solve another math problem very quickly. But unfortunately, we were relying on the hardness of this math problem in order to protect most of our secure data. Most encryption relies on the prime factors of integers in order to be secure. So in a world where quantum computers are quickly becoming a reality, it's clear that we need some other sort of solution that doesn't rely on the factoring of these prime numbers in order to be used. This is where a slightly more modern version of encryption called lattice-based encryption comes in. It's encryption that relies on very difficult math problems that involve mathematical structures called lattices. But what exactly is a lattice? Well, put simply, it's a mathematical structure that can be used to represent an infinite grid of points. Every lattice is formed from a set of basis vectors, and when you multiply those basis vectors together, they can form any point in the lattice. For example, if we have a 2D lattice with a basis of 0, 2 and 1, 0, it would look something like this. Now, this is a very simple two-dimensional example, but it's important to remember that a lattice can be comprised of an infinite number of dimensions and an infinite number of basis vectors. So, while it looks really simple right now, these things can very quickly get really complicated as you add to the number of basis vectors and dimensions. Now, in order to use lattices for encryption, we need to come up with a really hard problem that involves them. And the best problem we have so far is the closest vector problem. Put simply, the closest vector problem is when you're given a lattice, find the closest point in that lattice to any given non-lattice point. Now, what does that mean? So basically, if you have our lattice like we had before, and you pick a random point that's not exactly on the lattice, but is close to one of the points in the lattice, for example, this red dot here, we have to figure out what the closest black dot is to that red dot. Now, in this example, it's pretty obvious. It's this one right here. But once you add on to the number of dimensions and the number of basis vectors in your lattice, these problems can get really complicated really quickly. And what it essentially enables you to do is almost encode data into a secure lattice point that is really difficult to find unless you can derive the solution to this problem. There are a number of different encryption methods that utilize lattices in this way, in the form of the closest vector problem. Currently, the most widely accepted quantum-resistant lattice-based encryption algorithm is NTRU. The Latlock project allows anyone to utilize this novel form of quantum-resistant encryption in order to protect and safely transfer their data in the event of a quantum attack. So far, NTRU has stood out amid other types of quantum-resistant encryption as the fastest and most efficient solution. It is widely considered to be the best option for future encryption systems. Latlock is a prime example of NTRU's effectiveness and demonstrates how these cutting-edge technologies can be brought to the average consumer. Latlock is very straightforward to use. Just decide on a username and password you can remember and click Submit. From there, you're free to browse your computer for any files that you might want to secure, and encrypt and decrypt any of those files as you see fit. Once you close Latlock, any files that you secured will be safe until you log back in. Once a server architecture is implemented, you'll also be able to use Latlock to securely transfer files from machine to machine. Thanks so much for watching. I hope you learned something. If you have any questions at all, or if you're just looking to reach out to me, you can find me through my website, which is right here. And also, please feel free to like and subscribe if you enjoyed the video.